Okay, exercise 1002 is Euler's number, or E. Now that button's in your calculator, you've seen it before. Just like the pronunciation there, it's not Euler, it is Euler. We have to graph the derivative function of this curve. Okay, so we've got y equals a to the x. I haven't actually given any values. We're just going to sort of estimate the derivative function. So remember, the derivative function is the gradient. So if we look at this curve down here, the gradient's positive. Up here, positive. Up here, positive. Everywhere the gradient is positive. Down here, the gradient's really flat. So it's a really, really, really small number. So down here, I'm going to plot a really, really small number. Okay, the gradient up here is much, much steeper. It's a much bigger number. So I'm going to plot a much bigger number. The gradient down here is still pretty flat. Are you seeing already those 3 points that we actually get a really similar curve? The gradient of an exponential function is also an exponential function, which is pretty cool. Like in Desmos. So I've typed in the function f of x equals a to the x, and I've set a so it can vary from 1 to 5 as a slider. At the moment I have it set on 1, and 1 to the power of anything is always going to be 1. So we do have a horizontal line at y equals 1, or f of x equals 1. Clearly the gradient of this function is 0 everywhere. I've asked for the derivative, and if I turn that on, we can see there the gradient function is 0 everywhere. I'll just turn that off again. We'll come back to that in a minute. Now let's look at what happens when I change a. So if I increase a, I do get that exponential shape, like we've already seen. If you look at the y-intercept, that's always at 1. Now I can change that by, for example, if I just double everything, if I times the function by 2, then the y-intercept would be included in that, it would double. If I look at this point here, that's somewhere between 2 and 3, and put that 2 in front, that point has now doubled to somewhere between 5 and 6. If I was to make the if I make the x value negative, it will reflect it in the y-axis. If I make the whole function negative, it reflects it in the x-axis. If I do both, it's reflected in both axes. So it's well worth having to play with these yourself in Desmos as well. If I add 2 at the end, I shift the whole thing up by 2. If I subtract 2, I shift the whole thing down by 2. So those are some interesting ones to look at. Now I want to look a bit closer at the gradient function. So if I go back to a equals 1, as I said, the gradient now is 0 everywhere. If I increase a slightly, I get an exponential function, and you can see that the gradient is also an exponential function, but they're not exactly equal. Now when I make a bigger, they pass each other, and now the gradient function is up higher than the original exponential function. So one really interesting thing is to try and see where they're actually equal to each other. So if I just bring that back and try and get them to be equal, it's around about there somewhere, so that's 2.8. So I'm just going to get a bit closer here. Let's go maybe from 2.6 to 2.9. And I'm going to really zoom in on it because I want to see when they're exactly equal. Now you can see right now they're not exactly equal. They're close to each other, but they're not exactly equal. So at the moment the derivative function is above the original function, and if I decrease my value of a, they get closer and closer and closer and closer, and they just overlapped there. So around 2.7 is where they pretty much the same. So let's just zoom in a little bit more. Let's make that 2.7 and make that 2.73, for example. Oops, 2.73. Okay, let's zoom in a bit closer and see if we can get them a little bit more accurate. There we go. So around about 2.7184, they're pretty close. If I zoom in, it looks like they're pretty close, but you can see they're still not quite touching. So it's always fun to try and get them closer if you can. So that's 2.7182, which is pretty close. Now, by the title of this exercise, Euler's number, you might guess that Euler's number is that number where they are exactly equal to each other. And Euler's number is represented with the letter E, so e to the power of x. And now you can see that the gradient function and the original function are exactly the same curve. So we're just going to do some manipulation of exponential functions algebraically. So the first one is f of g of x. So I'm just going to replace the g of x firstly with 3 minus x. So it's f of 3 minus x. So we're just plugging 3 minus x into this function. So instead of x, we're putting 3 minus x. So that's e to the power of 3 minus x. Now, you can think about that as well in terms of e to the 3 times e to the minus x. Remember, when you're multiplying things, you add powers. You can also think of it as e to the 3 over e to the x. Same reason, you're subtracting powers, so that's like division, or you're just having a negative in the denominator. So those are some different ways you could represent that answer. The first one is just fine if that was the question. These are just out of interest. So g of f of x is the same as g of e to the x, because instead of f of x, I've put e to the x from up here. So then I'm just going to replace any x's in g with e to the x. So that would be 3 minus e to the x. Okay, this last one asks for h of 3 when h of x equals f of 2 times g of x. So firstly, I'm just going to have a little look at that. So h of x is f of, instead of g of x, I'm going to put 3 minus x. Now at this point we've got two choices. We could find what h of x is as a function, or we could plug in the 3 now if we wanted to. So I'm going to do it both ways. So f of x is e to the x, so any x in e to the x gets replaced with this. And then, so h of 3 is e to the 2, 3 minus 3 is 0, so 2 times 0, 2 times 0 is 0, anything to the power of 0 equals 1. The other way of doing it, as I mentioned, from this line, that would be the same as f of 0 by plugging 3 in here. And so that equals e to the 0, which equals 1. So same answer there. In example 2, bacteria are multiplying in a petri dish. The number of bacteria is given by n equals 100 e to the 0.04 t, where t is time in minutes. Find the initial number of bacteria. So that's just when t equals 0. So we just plug in 0 into here. So the number would be 100 times e to the 0, 0.04 times 0. E to the 0 is 1, so 100. And this style formula, that number at the beginning there is always the initial amount, but you do need to show that by subbing in the 0. The number of bacteria after 5 minutes. Now the key here is to check that we are in the same units. If this was in hours, we would need to adjust that. If they're not the same units, you do need to convert, and that kind of question does come up. But in this case, they are the same. So n equals 100 e to the 0.04 times 5. And if you put that into your calculator, that's approximately equal to 122 bacteria. Is this model realistic in the long term? No, it's not. The reason why is because there's always a limit in terms of how many bacteria are going to fit in the petri dish. Unless the bacteria are going to like explode out and take over the whole universe, there must be a limit somewhere. Something is going to happen externally to stop that growth. So no. So an example would be, if I put in, say, 1,000 minutes, there would be 2 times 10 to the 19 bacteria in that petri dish, and that's just unrealistic.